Welcome to the tutorial of Industrial Instrumentation. In this tutorial, we will talk about the introduction on Industrial Instrumentation. The context of discourse that we will cover in this particular tutorial are as follows. We will start with the functional elements of instruments. Then we will see the performance characteristics, statistical analysis, units of measurement, standards of measurement, signal conditioning, and lastly we will come to classification of instruments and measurement of industrial parameters. Instrumentation is that branch of engineering that primarily deals with three things: sensing, measurement, and control. Given below is the functional block diagram of an instrument system. The fundamental objective of instrumentation is in a process plant or environment is to collect data from different process parameters and to subsequently monitor the obtained values. Here we have an elaborate block diagram of an industrial instrumentation system. The main functional blocks are sensor, variable conversion element, signal processing block, signal transmission block, and finally the signal presentation or recording block. The measurement is first put through the sensor where the sensor senses the measurement and then it gives some output. This particular output is converted to a readable output form. Followed by that, the signal is processed so that it can be amplified, attenuated, filtered, and rectified according to the output reading element. The signal is further transmitted through a signal transmission unit, and finally at the readout we get the signal presentation. It can be recorded or it can be an instantaneous display. Considering biomedical instrumentation as part of industrial instrumentation, the measurement is nothing but human. Then we have the sensor block, which has two parts: primary sensing element or purely sensors and the variable conversion element or transduction elements. The next block is the signal conditioning block, which has three parts: power source, signal processing, and data storage. And finally we have the output or the display unit. For telemetry and other purposes we have data transmission. The stimulus that is put in the human body to carry out the specific measurements are radiation, electrical current, or any other form of energy. Here we see a very typical layout of a power plant. The main functional block in a power plant are the superheaters, the turbo set, the process control element, the transformer, the switch gear, the operations, the cooling tower, and the process control or the control panel. All these things, they are a subject in themselves of their own, but this is a schematic layout just to give an overview of how a power plant functions. If we specifically limit ourselves to thermal power plants, the different parts of a thermal power plant are depicted in this picture. The ID fan and the FD fan are two very important components in a power plant. The ID fan stands for induced draft and the FD fan stands for forced draft. Then we have the boiler, which has air preheater, economizer, and superheater. We have the turbine where the conversion from mechanical energy to electrical energy takes place, and then we have the generator from where the generated electricity is moved on to the grid element. We have a lot of other segments and sub-segments like condenser, CWP, coal handling plant, coal storage, ash handling plant, and ash storage. They all form part of the thermal power plant. The picture shows how a typical control room of any process plant looks like. The plant can be an oil plant, a power plant, or a mineral alloy plant, but more or less all the control rooms look the same. In any kind of electrical measurement, the four primary factors are voltage, resistance, current, and power. On the figure to our left, we see the relationship between these four factors, how they are interrelated. On the figure to our left, we see impedance and how impedance is denoted in terms of inductance and capacitance marked by L and C respectively. Before delving deep into the subject, let's classify instruments. Instruments can broadly be classified into three types: mechanical instrument, electrical instrument, and electronic instrument. The electrical instruments are further subdivided into two types, absolute or direct, indirect, and secondary or direct. The secondary direct instrument are further categorized as analog instrument and digital instrument. The analog instrument are further categorized as deflecting instrument or null deflection type. The deflecting instrument can be of three types: indicating, integrating, and recording. The entire industrial instrumentation relies on the performance characteristics of instruments. The performance criteria of any instrument is broadly categorized into four segments: the static characteristics, the dynamic characteristics, the static error, and the dynamic error. The static characteristics of an instrument are hysteresis, calibration, range, tolerance, stability, resolution, threshold, drift, which can be of three types: zonal, span, and zero, repeatability, reproducibility, linearity, sensitivity, precision, and accuracy. Under the dynamic characteristics comes the dynamic error, fidelity, speed of response, and instrument lagging. While the dynamic errors come under dynamic characteristics, the static errors can be classified as mistakes, systematic error, random error, and other error sources. The systematic error is further categorized as instrumental error or environmental error. The dynamic response is known as the order of an instrument, and the order of the instrument can be of three types: zero order, first order, and second order. Assuming y to be the dependent variable and x to be the independent variable, a zero order is numerically represented as yt equal to kxt. A first order system is represented as tau dy dt plus yt equal to kxt, and a second order system is represented as d2y dt2 plus 2 rho omega dy dt plus omega square yt equal to k omega square xt. The three figures below show a zero order system, a first order system, and a second order system response. Thus, to conclude, the order of a system is defined as the number of independent energy storage elements in the system, and intuitively by the largest order of the linear differential equation that describes the system. In a transfer function representation, the order is the highest exponent in the transfer function, as already illustrated in the previous expressions. A zero order system is a response that often means that the block does not alter the time response. All instruments behave as zero order instrument when they give a static output in response to a static input. For example, wired strain gauge. The system whose input-output equation is a first-order differential equation is called a first-order system. The order of the differential equation is the highest degree of derivative present in an equation. First-order system contains only one energy-storing element. Example: mass damper system, mass heating system, etc. A system whose input-output equation is a second-order differential equation is called a second-order system. There are a number of factors that make second-order systems important. They are simple and exhibit oscillations and overshoot. Examples are mass spring damper system and LRC circuits. Statistical analysis is significant as it permits analytical determination of quants of closing outcomes. Statistical analysis becomes strong with bigger number of sample size, therefore it demands a large number of measurement. Statistical analysis allows us to decide the best assessment possible for certain data and establish the restrictions of uncertainty intrinsic in a sporadic distribution of data. The parameters of statistical analysis are as follows: significant figure, collection of data, classification of data, measurement of central tendency, measurement of dispersion, measurement of skewness, normal or Gaussian probability curve, and data rejection. Each of the digits of a number that are used to express a result to the required degree of accuracy, starting from the first non-zero digit, is called significant figure. The process of gathering and measuring information on variables of interest in an established systematic fashion that enables one to answer stated research questions, test hypotheses, and evaluate outcomes is known as collection of data. The process of organizing data into categories for its most effective and efficient use is called data classification. There are three main measures of central tendency, which are mean, median, and mode. Each of these measures describes a different indication of the typical or central value in the distribution. The mode is the most commonly occurring value in a distribution. Common examples of measures of statistical dispersion are the variance, standard deviation, and interquartile range. Dispersion is contrasted with location or central tendency, and together they are the most used property of distribution. Skewness is a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. The skewness value can be positive or it can be negative or undefined. The qualitative interpretation of skew is complicated and unintuitive. Numerically, it is represented as S equal to mean minus mode by standard deviation. The median, mean, and mode of a normal distribution are equal. The area under the normal curve is always equal to 1. Normal distributions are denser in the center and less dense in the tails. Normal distributions are defined by two parameters, the mean, mu, and the standard deviation, sigma. Rejection of data. All data points should be retained that fall within a band around the mean that corresponds to a probability of 1 minus 1 by 2n. In other words, data points can be considered for rejection only if the probability of obtaining their deviation from the mean is less than 1 by 2n, where n is the sample size. Two factors are very important while conducting any measurement. First, the magnitude, and second, the unit of measurement. The units of measurement are broadly classified into the following types: fundamental units, derived units, absolute units, CGS unit, MKS unit, SI unit, and English system of units. All industrial measurements are categorized within these standards of measurement. The first are the international standards, from where the primary standards are derived, from where the secondary standards are derived, from where the working standards are derived. Industrial measurement requires a lot of signal conditioning for careful validation of the data. The different types of signal conditioning are signal amplification. Reverse phenomenon is called attenuation. The signal amplification can be mechanical amplification such as gear, lever, or combination of both, hydraulic or pneumatic amplification, optical amplification, electrical amplification. Then we have signal filtration, that is removal of unwanted noises. It can be mechanical, pneumatic, or electrical. We have signal compensation and signal linearization. We have signal differentiation and integration. Then we have analog to digital and digital to analog conversion. And finally, we have signal averaging and signal sampling. As previously already mentioned, instruments are largely categorized as absolute and secondary instruments. Now, under the secondary instruments come three types of instruments: indicating instrument, recording instrument, and integrating instrument. As part of industrial instrumentation, we focus on the secondary instruments. For proper understanding of any measurement system, one must understand and know the following issues: the basic principle of operation, the block diagram of the instrument and the setup, the schematic diagram of operation, the range of the instrument, the pros and the cons of the instrument. There are several factors which are measured as part of industrial instrumentation. The four major parameters are flow, level, temperature, and pressure. Other important factors are density, viscosity, pH, and conductivity. Before we delve deep into industrial instrumentation, let's have an introduction of process control. Here we see a block diagram of a process control system that shows the cause and effect relationship between the input and the output of the physical system. A block diagram provides a means to easily identify the functional relationship among the various components of a process control. It starts with reference input and ends with controlled variable output. In between we have the control element and we have disturbances or noises in the plant. The actuating signal is acted by the control element to produce the manipulated variable, and after introduction of the disturbances we finally get the controlled variable. This is a feedback system and the output variable is again fed to the input terminal to have a constant check and monitor the signal response. A plant is a system or process through which a particular quantity or condition is controlled. This is also called a control system. Control element is the component needed to generate the appropriate control signal applied to the plant. These elements are also called controllers. Components needed to identify the functional relationship between the feedback signal and the control output is called the feedback element. External signal applied to the summing point of the control system to cause the plant to produce a specified action is known as a reference point. The signal represents the desired value of a controlled variable and is also known as the set point. Quantity or condition of the plant which is controlled is known as the controlled output. This signal represents the controlled variable. Function of the output signal is known as the feedback signal. It is sent to the summing point and algebraically added to the reference input signal to obtain the actuating signal. The control action of the control loop is known as the actuating signal and it is equal to the algebraic sum of the reference input signal and the feedback signal. It is also sometimes known as the error signal. The variable of the process acted upon to maintain the plant output is known as the manipulated variable at any desired value. An undesirable input signal that upsets the value of the control output of the plant is known as disturbance or noise. PID stands for proportional, integral and derivative algorithm. This is not a PNI, which is a piping or process and instrumentation diagram. Then we have PV, which stands for process variable, a quantity used as a feedback typically measured by an instrument, also sometimes called MV or measured variable. We have SP as the set point or the desired value of the PV. OP represents output, a signal to a device that can change the process variable frequently, a valve, a damper or a pump speed reference, also sometimes called CV or control variable. Overshoot is when the process variable moves farther past the set point than desired. A PID loop in manual only changes its output upon operator request. A loop in remote has its set point automatically adjusted by external logic. In local, the set point is only changed by the operator. Some systems combine auto and remote into cascade mode to control the set point. A direct acting PID loop increases its output in response to increasing process variable, while a reverse acting loop decreases its output. Normal loops are reverse acting. Loops controlling level or pressure via a valve on an output or temperature via cooling are generally direct acting, which is known as backwards loops. The difference between the process variable and the set point variable is known as the error. Now that we have covered all the basic terms and terminologies of a process control block, here again we see a general control loop of a process control. We have the set point, we have the process variable, in between we have the disturbance from the process itself, we have the final control elements called actuators that are regulated by the controller based on the set point conditions. The measurement sensors and transmitters bring the output process variable back to the set point for a feedback process loop. Here in this picture, we see a very conventional response of a PID diagram, where Kp, Ki and Kd are the proportional gain, integral gain and the derivative gain. We'll come to these topics when we go into process control system in greater detail. The final control elements or actuators are an important part of the process control system. They are the elements on which the controller acts so that the measured variable can be in parity with the set point variable. Given below is a different type of valves that are used in the process industry. There can be gate valves, globe valves, ball valves, butterfly valves, diaphragm valves and safety valves, which have again their own different types and classes. The major valve types are butterfly valve. The closing mechanism is provided by a disc that sits in the middle of the valve body and rotates. When the level is turned, this disc moves sideways or upright to allow or block the flow of water. Then comes plug valve. There is a cone-shaped plug inside the valve body that moves aside when the handle or wheel is turned. The third important valve is needle valve. There is a sliding needle to regulate flow of water or other fluids. It is a very precise valve and is used in engines such as central heating systems and automotive carburetors. The fourth major valve is gate valve. A metal gate raises or lowers regulating flow of water. Most valves in this design are kept either fully closed or fully open. Its purpose is not for partial closing or opening. It is mostly used in water supply pipes. The fifth type is the globe valve. The most common example of a globe valve is water faucet. When the handle or wheel is turned, the blocking part moves upward or to allow the water to flow. Unlike a gate valve, you can easily regulate the flow of the water. And finally, the ball valve. A rotating ball that has hollow core operates in the center of the valve body. When the hole is parallel to the pipe, water will flow. When the hole is perpendicular to the pipe, water flow will stop. The next important part in process control is electrical switches. The electrical switches are of different types. One of them is solid state switch. Solid state switches are electric devices that do not have moving parts to wear out. They are able to switch faster without sparking between contacts or problems with contact corrosion. However, the disadvantage includes high cost and high current rating. The second type of electrical switch is the electromechanical switch. They have mechanical contacts or relays. These types of switches can control a wider range of current and voltage. They are not affected by dirt, mist, magnetic field or temperature ranges from near absolute to almost 1000 degrees Celsius. Electromechanical switches can adapt to misalignment in installation application to ensure there is no leakage current and making it available in many circuitry, actuator and housing styles. The disadvantage of electromechanical switch includes their price, limited contact life, large size and slow response. When selecting a level switch, the user needs to determine if the electric circuit requires a normal open or a normal closed switch. Normal open, denoted by NO, switches do not allow current to pass through in the free position. They need to make a contact to be activated. The normally closed, marked as NC switches allow current to pass through in the free position and need to break contact open to be activated. Most switches have one or two poles and one or two throws, but some manufacturers will produce custom level switches for special applications. The number of poles describes the number of separate circuits that can pass through the switch at the same time. The number of throws describes the number of circuits each pole can control. This is noted by the configuration of the circuit, that is NO or NC, that is normally open or normally closed. Breaks are interruptions to the circuit caused by the separated contacts that the switch introduces into its circuits. It opens or interrupts the circuit in the process. Single pole single throw SPST switch makes or breaks the connection of a single conductor in a single branch circuit. They usually have two terminals and are referred to as single pole switches. Single pole double throw SPDT switches make or break the connection of a single conductor with either one of the two other single conductors. They usually have three terminals and are commonly used in pairs. SPDT switches are sometimes called three-way switches. Double pole single throw switches make or break the connection of two circuit conductors in a single branch circuit. They typically have 6 terminals and are available in both momentary and maintained contact version. Double pole double throw DPDT switches make or break the connection of two conductors to two separate circuits. They typically have 6 terminals and are available in both momentary and maintained contact versions. Here in the picture below we see the different setups of SPST, SPDT, DPST and DPDT switches. The first one shows single pole single throw single break. The second one shows single pole single throw double break. The third one shows single pole double throw single break. Fourth shows single pole double throw double break. The fifth one shows double pole single throw single break. Next we have double pole single throw double break. Next we have double pole double throw single break, and finally we have double pole double throw and double break. A single pole single throw toggle switch connects or disconnects one terminal to or from another. It is the simplest switch. A single pole double throw toggle switch connects a common terminal to one or the other of two terminals. It is always connected to one or the other. The two outside terminals are never connected by the switch. A double pole double throw toggle switch acts exactly like two separate SPDT switches connected to the same switch bar. It has two separate common terminals and each of these is connected to one or the other of the other two terminals on the same side of the switch. The dotted line in the picture is to illustrate that the switch is actually two SPDT switches in one package with one switch bat. Here we see the symbolic representation of SPST, SPDT, DPST and DPDT switches, and finally we have DIP switches. For more detailed reading, the viewers can refer to the following references. I hope this has given the viewers an elementary idea of industrial instrumentation and process control. Thank you.